And I think a good place to begin, we were in like the middle of a proof of something last time, right? We were in the midst of proving this inequality, that if you have two bounded functions, f and g, on a closed bounded interval a, comma, b, then the sum of the low-order Darboux integrals is less than or equal to the low-order Darboux integral of the sum. And what we had managed to prove so far, so at this point, maybe I'll write it sideways, we have s minus of f comma delta plus g minus of f comma, god damn it, s minus of g comma delta is, well, bigger than or equal to, well, then I should write it this way, is bigger than or equal to s minus, no, I have the sum of the two is less than or equal to the thing corresponding to the sum. Is less than or equal to s minus f plus g comma delta. That's what we have so far. And maybe a good place to begin is let's remember all of the definitions. So I'm even going to write these here. So let's start with the s's. So let's let, so I'm going to write things that you already know. Let's let f be a bounded function. And delta equals a subdivision of AB. And maybe it's actually useful to write it as J1, J2, on up to some Jn. Then let's write down some notions. So let's see, what was little m of f comma j? What did we establish that as being? What did we set that equal to? Possibly by looking back on like page 1 of the note packet.
The infimum of the set of elements f of x where x is in j.
Good. And I just said what we managed to pull off last time is we proved something about s minuses. Let's remember what s minus means. What is s minus of f comma delta? Well, it's the lower Darboux sum, so it's probably a sum of something.
The sum of the m of f j's times the length of j for all of j's in delta.
Yeah. So each of those gives us like a lower bound on the area under the curve, whatever the area under the curve should actually mean. And when we took like the supremum of all of those areas under the curve, we got what was called the lower Darboux integral. So what is the definition of the lower Darboux integral?
The supremum of all the s of minuses of f deltas.
Yeah. Cool. So let's just recall what happened last time. So let's just try to convince ourselves of something. So right now we've shown that the lower Darboux sums satisfy the inequality we want to prove about the integrals. So that should be like pretty convincing, right? The integral is like defined by all of the sums. We've shown that all of the sums satisfy the inequality, so it should follow quickly for the integrals. And let's just go through the proof. So as you've told me, the lower Darboux integral is the supremum of all of the s minus of f comma deltas. Same thing for the lower Darboux integral of g. Those are both least upper bounds. Now what I'll do is I'll go for the definition of supremum in terms of some epsilons. And let's just draw a picture to remember how it should go. So I'll figure out what should go there by like drawing the picture. So here is the lower Darboux sum, which is a supremum of some stuff. Then it should follow that for every epsilon bigger than 0, where should I be able to find one of the things in the set that that's a supremum of?
Could you repeat your question?
Yeah, so this is the supremum of something. So supremum of some set. I'll just call that set x right now. Does it follow that there should exist an element of x in this half of the interval? No, because then this would not be an upper bound. Should it follow that there should be something in x in this half of the interval? So that means that there must be some thing of the form s minus of f comma delta in between the lower integral minus epsilon and the lower integral itself. So let's write that right here. So that means that the lower integral minus, well, I'm going to make it epsilon over 2 because I'm going to add 2 of these things together, is less than some s minus of f comma delta is less than or equal to the lower integral of f. And there exists some other subdivision, delta prime, such that the lower integral of g minus epsilon is less than or equal to s minus of g comma delta prime. Is it clear why I have to take 2 different subdivisions? So I know that there's some subdivision that gets me really close to this lower integral. I don't know which subdivision it is. I know there's some other subdivision that gets me really close to this lower integral. But just because I know 2 different things exist doesn't mean they're the same thing. Like how in an appeal to the mean value theorem, if you're applying the mean value theorem to some f and some g, you'll get 2 different values of c, one for f, one for g. Same thing here. An existential argument doesn't give you the same subdivision each time, but I really want the same subdivision each time. So if I have 2 different subdivisions, how can I get a single subdivision that's like better than both of them?
Common refinement.
Yeah, they have a common refinement. So those 2 subdivisions aren't the same. I want them to be the same. By proposition 5, they have a common refinement. By proposition 4, this refinement is better than either of them. And let's remember what better means. Which way should those inequalities go? Possibly by looking back at the statement of the proposition. Is this bigger or is the refinement bigger?
Refinement.
Yeah. Because like, these things are supposed to be lower bounds. A better lower bound is a bigger lower bound. Aha! So now I have a single subdivision, single subdivision to work with, delta double prime. Nice. Oh, interesting. Is that just like the same thing again? Yeah, I think there was like a copy paste and failure to proofread error here. So I have these two subdivisions and the single common refinement. So I guess there's like a summary of what we just got above anyway. Let's see what we can do with these. So let's look at everything in sight there and see what we can get. I suggest adding the left halves. So I can conclude now that the lower integral from a to b of f dx plus the lower integral from a to b of g dx minus epsilon is less than s minus of f comma delta plus s minus of g comma delta prime, just by adding those together. But let's see, like I said, I want to replace this with like a single subdivision, and I can, right? Delta double prime is that single subdivision. That is now less than or equal to s minus of f comma delta double prime plus s minus of g comma delta double prime. Do I have a result that allows me to compare a sum of two s minuses with an s minus for the sum? And it's not like a proposition that I'm looking for, it's something that I did earlier on this very proof, like at the end of last time. What's the last inequality we verified?
The sum of the s minuses is less than or equal to s minus the sum.
And I think that I'm going to come back and use this line by the end. But let's see. All of the s minuses are supposed to give lower bounds on the area under the curve. So how should this compare with the actual integral of f plus g? It should be less than, or maybe equal to. Possibly because, right, the lower integral is an upper bound on all of the s minuses. That's less than or equal to the lower integral of f plus g dx from a to b. Oh, cool. So that means the lower integral of f plus the lower integral of g minus epsilon is less than or equal to the lower integral of f plus g for absolutely every positive number epsilon. And as soon as you get an inequality to hold for an arbitrarily small epsilon, what can you do? What can you conclude? You can conclude that epsilon where epsilon, you can conclude that inequality holds when epsilon is equal to 0. So the lower integral from a to b of f plus the lower integral from a to b of g is less than or equal to the lower integral from a to b of f plus g dx. So that's like, well, there's still one inequality in this claim I was in the midst of proving that we haven't done. There's the same inequality for the upper integral. Do you think the proof will probably be pretty similar? Yeah, I think like all of the inequalities will be opposite because you'll be using the things that are you'll be using that big N is a sup instead of an inf. You'll be using that the upper integral is an inf instead of a sup. And otherwise it'll be the same proof. So some of the plus epsilons will be minus epsilon, some of the greater thans will be less thans. How do people feel about that? That proofs seem okay? So let's like go through the list of the lot of them again. So this one says that the lower Darboux integral is what's called superadditive. the upper Darboux integral is sub-additive. When you combine two intervals together, both of the integrals behave the way they should. They're additive on the nose. When you multiply a function by a positive constant, the lower Darboux sum integral behaves exactly how you think. The upper Darboux integral behaves exactly as you think. And right, that should be the case because that should happen for like the sums themselves, right? If you multiply by a negative number, then the lower Darboux integral becomes the upper Darboux integral, and that makes sense. When you multiply a number by when you multiply an inequality by a negative, it flips. That's why this was confusing me last time. That is stated correctly. If you have some functions that satisfy some inequality, so do the integrals. Which way they have to. So I'm not going to go through the proofs of the rest of them, but I will, however, go through an application of the rest of them. So I know something about the upper Darboux integral and the lower Darboux integral. I call a function integrable when the upper and lower integrals are the same. So suppose you have a bunch of integrable functions, and you add up the two integrable functions. You add up the integrals of the two integrable functions, then you get the integral of this. What do you think? Do you believe that? Yeah. Oh. Why should that happen? Well, this is the same thing as the sum of the lower integrals, which should then be less than the lower integral of the sum. But they're also the upper integrals. So this should be greater than the upper integral of the sum. So that shows that the upper integral of f plus g is less than or equal to this, is less than or equal to the lower integral of f plus g. But you already know that the upper and lower integrals already satisfy the other inequality, so those two upper and lower integrals are the same. That was all said in words, but people follow that chain of ideas? Yeah. Why does this happen? Well, it happens because it's true for the upper and lower Darboux integrals. So the upper and lower Darboux integral of this is the same either way, so h is integrable, and you're done. If you take a function and you multiply it by a constant, well, between the two cases, you get that the same thing holds for upper and lower Darboux integrals, so of course it holds for the integral, and the same thing for the fourth. So as long as a function is Darboux integrable, you get lots of good things for it, but have we actually verified that any function is integrable at this point? No. I don't know, from like calculus, what sort of functions do you think you can take the area under the curve of?
Constants.
How to be able to take the integral of a constant function? So if this theory does not predict the area underneath a constant, underneath the graph of a constant function, it's no good. So constant functions had better be okay. What other things can you probably integrate?
Linear functions.
Yeah, you can probably integrate linear functions. In fact, if I draw like a continuous function, you can probably like shade in the area under the curve, so you better be able to compute that area. So one of the things that we will prove today, in fact, the last thing we'll prove today, is exactly that. If you have a continuous function on a closed bounded interval, then it has a Darboux integral. Then it's Darboux integrable. The upper and lower integrals are the same. So anything continuous should be okay. What sort of things do you think might not be Darboux integrable?
Indicator function of the rationals.
Yeah, how about the indicator function of the rationals? What is the indicator function of the rationals? Look at the example at the bottom of this page. Actually, maybe not quite that. It should be 0, not -1. That's okay. So here's a function which is 1 whenever x is rational, -1 whenever x is irrational. I claim that this is not integrable. And I did it over the interval from, say, 0 to 1, just to be explicit. So let's try to believe that. The actual proof is homework, but maybe I'll give some ideas. So let's actually take any subinterval j. So tell me, in that subinterval, are there both rational and irrational numbers? Yeah. By a result proven in Math 316. So tell me, remember m is like the infimum of all of the function values in J. What's the infimum of all of those function values then?
-1.
-1. So that should mean something like s minus of f comma delta. I haven't quantified anything, but I'm not actually giving the proof. Delta is this subdivision. That should be like the sum over all of these j's of a bunch of m's, but all of the little m's are -1 times the length of j. So that's just negative the sum of all of the lengths of the components of a subdivision. Well, you can pull the -1 in, right? That's a constant. That's a constant in the sum. If you add up all of the lengths of a subdivision of the interval from 0 to 1, what should you get? You should probably get 1. So all of the subintervals result in a lower, all of the subdivisions result in a lower sum of -1. What's the supremum of the set that only contains -1? -1. So what's the lower Darboux integral? -1. Do you think you could similarly show that the upper Darboux integral is +1? Yeah. So all of this technique tells you that the area underneath this curve should be somewhere between -1 and +1. And the payoff, if you like tried to graph this function, right, be like, oh, so it's going to be like 0 and not -1 and +1 all over the place. I'll never actually manage to graph it. Graphing something like that. Because I can't tell the difference between a rational and an irrational number without looking really, really close. So indeed, like, you can't make sense of the area. But that seem reasonable? So there are lots of examples of non-integrable functions. They just happen to look maybe a little bit perverse. So let's start proving that some things are integrable. Let's prove in particular that every continuous function is integrable. Because this is definitely not a continuous function. Well, in order to prove that, I will need the following result, which will give me a handier way of checking if a function is Darboux integrable than computing the lower Darboux integral and the upper Darboux integral and showing that they're the same. Because computing either one of those in an example that's even a little bit complicated is going to be really, really hard. And so to compute two things, both of which are really hard to understand, and say whether they're the same is going to be super difficult. So let's instead just let's check this instead. So a bounded function f from a to b is Darboux integrable if and only if for every positive number epsilon there is some subdivision so that the upper Darboux integral, which remember is always bigger than a lower Darboux integral, but it is less than the lower Darboux integral plus epsilon. So a function is Darboux integrable if you can make the upper and lower Darboux sums pretty close. Which makes sense, right? It says that whenever you get an upper bound, you also get a lower bound that's like pretty close. So you don't have any freedom. It pins down the value. All right, so this is an if and only if statement. So if you want to prove an if and only if statement, you have to prove like two things. Let's prove one direction first. Let's assume that this function is Darboux integrable. What does it mean to be Darboux integrable?
The upper and lower Darboux integrals agree.
The upper and lower Darboux integrals agree, and then we call that same thing the Darboux integral. So the integral from a to b with a line on top of f of x dx is the same thing as the integral from a to b with a line on bottom of f of x dx. So what does this mean? This function is simultaneously the supremum and the infimum. It's well, different things. Okay, say it one at a time. It's the infimum of the set of all upper sums. So that means we should be able to find an explicit subdivision for which that upper sum is a little bit less than that integral. So I should be able to find a subdivision delta so that the Darboux integral, which is the same as the actual, the same as the upper Darboux integral, there. And I'll have to redraw the picture each time, right? So the upper Darboux integral is the infimum of some things. So on which half of the integral should I see one of the elements? So that means I should be able to find a subdivision with upper integral less than or equal to s plus, I'm leaving out all the things, this is the scratch stuff, less than or equal to upper integral plus a small number of epsilon. Fair enough. So that means that I now have subtract epsilon from everything. The upper integral is bigger than or equal to the upper sum minus epsilon. And maybe that I'll replace that epsilon with an epsilon over 2. But I think that's really more of an analysis 1 thing to do. I think I'll be happy winding up getting to the end and saying that an inequality holds with a 2 times epsilon for an arbitrarily small epsilon. So we're still happy. I don't think I'll bother dividing it by 2. If you read an actual analysis paper, they'll do it for an arbitrary epsilon, and they'll wind up with like a 4 times epsilon at the end, and then they'll say, oh, by dividing epsilons by 4, the proof is complete. Okay, similarly, this thing is the supremum of the set of all lower sums. So there should be some other subdivision, not necessarily the same subdivision, delta prime, such that what sort of inequality should hold? Sorry about you guys to draw this sort of picture on your own right now. What sort of inequality do you get? So this time I'm thinking of it as the lower interval, which is a supremum. So which half of the interval do I see stuff in? So that means I have this subdivision, I don't know, corresponds to some delta prime, such that the lower integral minus epsilon is less than one of the s minuses, is less than or equal to the lower integral itself. Adding epsilon to everything in sight, it looks like I get the lower integral, which is the same as the integral, is less than or equal to an s minus plus epsilon. So the integral is less than or equal to s minus of f comma delta prime plus epsilon. So let's see what I have right now. I have right now s plus of f comma delta minus epsilon is less than or equal to the integral of f dx is less than or equal to s minus of f corresponding to delta prime plus epsilon. So from that green inequality, could we deduce that exactly? But could we deduce that almost anyway? Like with the 2 in front of the epsilon, we definitely have it. So, I don't know. Either we can divide the epsilons by 2, or I can put a 2 in front of that epsilon. And let's leave it to a choice, because either way, I'm sure that the notation will be screwed up later on. Divide epsilons by 2. Put a 2 next to that epsilon. Okay. That's not the way I was expecting that vote to turn out. Oh, wait, but that almost gives us the result, right? We needed to show that there exists a single subdivision for which s plus and s minus are pretty close. Right now we have 2 different subdivisions for which s plus and s minus are pretty close. What should you do when you have 2 different subdivisions?
Common refinement.
So there exists a common refinement, delta double prime. Let's take a look at proposition 4 and the inequalities we currently have to try to put these in correct order, from smallest to largest. Oh, well, I guess I'll also replace all the epsilons with 2 epsilons so that we can use that inequality. You guys said you would rather have 2's in front of the epsilons. So there's the inequality I already have. By referencing proposition 5, what other inequalities do we know? Here are the other 2 things I need. So, right, informally, when you take a refinement, you get better bounds. Both of these are upper bounds. What does it mean for an upper bound to be better?
Lower.
It's lower. And hopefully that's also what the proposition tells you. Here's a lower bound. Here's a better lower bound. What does it mean for a lower bound to be better?
It's bigger.
It's bigger. Hey, wait, does that mean this is less than or equal to that? In fact, strictly less than, right? So, s plus of f comma delta double prime is less than or equal to s plus of f comma delta. Is less than or equal to s minus of f comma delta prime is less than or equal to s minus of f comma delta double prime. Plus 2 epsilon plus 2 epsilon. Hey, have I just shown that there exists a single subdivision for which s plus and s minus are pretty close to each other? Yeah, that's exactly what the theorem says. So that's half of the proof. Let's do the other half of the proof. Let's assume that for every epsilon there exists a single subdivision delta such that s plus is less than or equal to epsilon plus s minus. my goal, want to show that the upper integral of f dx is equal to the lower integral of f dx. Now remember, we're analysts here. If we're going to prove equality, one good way is by proving two different inequalities. Do I already know one of those two inequalities is true? Yeah, I know that the lower one is less than or equal to the upper one. Not because it's obviously that way, but because we've actually proven it. We already have this inequality. Let's try to prove the other inequality. Let's prove that this is less than or equal to that. And let's see what that means. I want to prove that this is less than or equal to that. Well, this quantity, by its very definition, is the infimum of something, right? It's the infimum of all of the s pluses. So that means that this thing is a lower bound on the set of upper sums, and this is an upper bound on the set of lower sums. So that means the upper integral is less than or equal to s plus of f comma delta, where here, have I declared an explicit choice of delta? Or have I forgotten to declare a variable? Assume for every epsilon bigger than 0, there exists a subdivision. So I have a single subdivision in mind. And it's the subdivision which gives me this. So I always know this is true. I always know this is true, because right, the lower sums are always less than or equal to the integral, because the lower integral is the least upper bound on the set of all lower sums. This inequality was assumed. Hey, wait, so I now know that the upper Darboux integral is less than or equal to the upper Darboux integral plus epsilon for absolutely every epsilon bigger than 0. Hey, does that just give me the other half of the inequality? So, the upper integral is less than or equal to, well, okay. As we see that that holds for every epsilon bigger than 0, we can erase the other inequality. Was that the other inequality that we needed to show? Whew, that's it. By proposition 7, we already had that the upper integral of f dx is bigger than or equal to the lower integral of f dx. So we conclude that the upper integral of f dx is equal to the lower integral of f dx. So f is integrable. All right, so let's, like, the proof is out of the way, so let's go back to the statement and see if we can unpackage what it says. The theorem says that if we can find or finite a subdivision so that the upper bound on the area we get isn't much bigger than the lower bound on the area we get, then the function itself is integrable. Well, one way of doing that is, well, what if we could find some subdivision so that whenever you looked at any element of the subdivision, every y value over that interval was pretty close to each other. That would do the job, right? What sort of functions do you have the property that if you look in a really, really small interval, the function values in that interval don't change very much?
Continuous ones.
Yeah, continuous ones. Right, that's exactly like, if you made sense of it, that would be a statement of, well, uniform continuity.
Mm-hmm.
But over closed bounded intervals, does the word uniform add anything? That's a weird question. Is it true that every continuous function is uniformly continuous on a closed bounded interval?
Yes.
Yes. So let's prove the next result. Let's prove if f from a to b to r is a uniformly continuous function with uniform in parentheses, because I'll use the word uniform in the proof, but every continuous function is uniformly continuous. Then that function is integrable. So let's do the proof. So let's let f from a to b be any uniformly continuous function. It's a corollary of this theorem, so I'm going to prove this condition, that for every epsilon there exists a subdivision for which something happens. So I'll consider any epsilon bigger than 0, and I need to come up with a subdivision that's good. So the only assumption I have right now is continuity. So let's consider any epsilon bigger than 0. Then it would follow that I'm not just going to want an epsilon at the end, although we could, and then just like figure out what we need to divide that epsilon by. Then something positive multiplied by epsilon is also bigger than 0. So by uniform continuity, there exists a delta bigger than 0 such that, what's the statement of uniform continuity?
For all epsilon greater than 0, for all x in the domain, there exists.
No, I'm going to write down exactly what you said, and then we'll figure out.
Oh God. So then I'd like to retract my offer.
No, you said for all x last.
Which I think is wrong.
Because the whole purpose is that you remove the
Oh.
for all x before the after
Right.
the delta and before the delta.
Gotta think it through. Right, so it has to work for all. One choice of delta for all the x.
Yeah, so you guys have already walked it out, right? Like the problem with this is this delta can depend on that x, which is what uniform is supposed to not mean. It has to be the same delta for every x. So how do you fix this? Okay. So since this function is uniformly continuous, and we've picked a positive number in that red box, it follows then that there exists a delta bigger than 0 such that for all x and y in the interval from a to b, if the absolute value of x minus y is less than delta, then the absolute value of f of x minus f of y is less than whatever we figure out should go in this red box. Nice. So that means as long as we only ever consider x and y values that are within a delta of each other, we're happy. Well, let's use that to pick our subdivision. Let's pick a subdivision, J1, J2, J3, J4, so that all of those subdivisions have lengths less than delta. Okay, cool. So by the extreme value theorem, right, this function is continuous, and though each ji is a closed bounded interval, so we can appeal to the extreme value theorem on each ji. By the extreme value theorem, little m of ji comma f and big M of ji comma f are both in what interval? Who remembers the statement of the extreme value theorem? The extreme value theorem says that if you have a continuous function on a compact set, that the supremum
Yeah.
Yeah.
so in what set do I know that little m of f comma ji lives?
F of J I.
F of ji. So there exists some inputs, x and y, in ji, so that little f of x is little m of ji comma f, and little f of y is big M of ji comma f. I feel like at this point I've probably switched where the j's and the f's have gone in my notation. But, I mean, well, okay, because one of them is a function, the other one is a set. So it's clear from context how to fix what I have done. Nice. So this x and y are both in ji, and the length of ji is less than delta. So what can you tell me about the difference between f of x and, okay. So since both of these are in ji, length of ji is less than delta, how far could x and y possibly be from each other? Length of ji, which is less than delta. So the absolute value of x minus y, that's less than or equal to the length of ji, which in turn is strictly less than delta. Oh wait, but I picked this delta with something in mind. So that means that f of x minus f of y in absolute value is less than a number in a red box. So in particular, we see that for every delta bigger than 0, 0 is, well, less than or equal to big M minus little m is less than whatever number we decide to eventually put in this red box. All right, now let's go back to what we actually wanted to check. We wanted s plus and s minus to be pretty close to each other. So that means I want s plus minus s minus to be fairly small. In fact, less than epsilon. So let's try to understand what that means. So s plus minus s minus. Let's see, that's going to be a sum over all of these j's in delta of big M of f comma j. I'm going to do the factoring. Do people want me to write out the full sum and then like the two different sums and then combine them into a single sum? I'm going to do that. Times the length of j minus the sum of all the little m's times the length of j. Pretty happy right now? Let's simplify this. Let's combine those. Let's write it as a single sum and do some factoring. I could rewrite that as the sum of a bunch of j's of big M of f comma j minus little m of f comma j multiplied by the length of j. Do I have a bound on how big big M minus little m is? Yeah, whatever we pick. It's the thing in the red box. Oh wait, that's like the McDonald's movie rental system, right?
McDonald's does not own it, but yes.
Is red box even a thing anymore?
I don't know.
Yeah.
Okay, cool. So it's less than that. All of these are constants, right? They're the same for each j, so I can pull that right on out. If you take a subdivision of the interval from A to B and add up all of the lengths, what do you get?
B minus A.
The length of the whole interval. That's actually something that you're going to prove in one of the homeworks for today, because I realized I was using it an awful lot without justifying it. The proof is stupid easy. I shouldn't say that. The proof should be pretty straightforward. So that's box times the length of the interval from A to B, well, B minus A. So what do I want to put in that box if I want this to be less than epsilon? Epsilon over B minus A. That is now equal to epsilon. And I don't think I'll fill in all of the boxes in the interest of time. So what have we done? We've considered any epsilon bigger than 0. Since epsilon over b minus a is positive, we found a positive number, little delta. We used that little delta to come up with a subdivision, big delta. And we proved for that big delta, s plus of f comma delta minus s minus of f comma delta is less than epsilon. So s plus of f comma delta is less than epsilon plus s minus. So by Theorem 12, it follows that this function is integral. Do you think that only continuous functions should be integrable, or should there be other functions which are integrable?
Probably other functions.
Yeah. I mean, I guess if the idea is integrable is you should make a field to make sense of what the area under the curve is. Do you think you could probably figure out what the area under that curve is? Yeah. Because you would compute this area and then that area. And in fact, don't we have a theorem that says that that gives the integral from A to C?
Yeah.
Do you think if you had a function that was like continuous, except like at this point it failed to be continuous. Should that still be integrable? Like, do you think if there were finitely many discontinuities like that, the thing would still be integrable? So you have some freedom in what functions are integral. Cool. So I'm at time. I don't have an office hour after this class today, do I? Is it in the past? Anyone planning on coming by my office to talk to me? Okay.
What? No. I know. Yeah.